Jai Hind everyone. Myself Dr. Sharma from AKGEC Engineering College. The subject which today I am going to take, that subject is laser system and application, and this particular subject is under science based open lecture subject, and the topic which today I am going to take, that topic is related to coherence. Since this subject is related to laser, and when we are saying laser, then we are referring that highly coherent light which is having high intensity, high brightness, high monochromaticity as compared to ordinary light. The most important property of laser, because of which it is superior as compared to ordinary light, that property is known as coherence. So when I'm saying coherence, then what is the meaning of this term coherence, that we are going to discuss in today's lecture. So in today's lecture, we are going to discuss about the coherence, that what is the meaning of coherence in case of light. After this, we will discuss two different type of coherence, means we will discuss two different aspects of looking this term coherence. The first type of coherence, which is related to time actually, that coherence is known as temporal coherence. The second type of coherence is spatial coherence, which is actually related to distance, or that is coherence in space. So in other words, we can say that temporal coherence is coherence in time, whereas spatial coherence, that is coherence in space. So what is the meaning of this temporal and spatial coherence, and what are those parameters which are going to decide temporal and spatial coherence, that we will discuss in today's lecture. So when we are saying coherence, then the meaning of this coherence is, if you have two light rays, then those two light rays, they are said to be coherent if the phase difference between those light rays is either zero or constant. Means when we are saying coherence, then we are actually referring the phase difference between the light rays. So coherence means either the phase difference is zero or the phase difference is constant. Or in other words, I can say, if we have a light source, then from that light source, you will get perfect sinusoidal wave. The light which is coming from any source, that will be in the form of these sinusoidal wave. So if there is crust to crust or trough to trough correspondence, means if one of the light ray, if there is crust to crust correspondence with another ray, trough to trough correspondence, then you will say there is perfect phase relationship between those light radiations. So as you can see here, we have these two sources. From this particular source, you are getting this perfect sinusoidal behavior. And if you have an ideal source, then that ideal source can maintain perfect sinusoidal behavior for infinitely. So what I am trying to explain here, for every source, there is some finite time up to which we can get perfect sinusoidal behavior. So that time up to which we have that perfect sinusoidal behavior, that time is known as coherence time of the source. So as you can see here, if the phase difference is zero or the phase difference is constant, then we will say that there is perfect coherence between the light rays. As you can see in this picture, these light rays, they have perfect phase relationship. Why I am saying there is perfect phase relationship? Because there is crust to crust correspondence, as well as there is trough to trough correspondence. So if you will find the phase difference between these light rays, then that phase difference will be either zero or constant. But if you will take this particular case, as you can see here, these light rays, they are not having any fixed phase relationship. There is no crust to crust or trough to trough correspondence here. So these light rays are incoherent in nature, whereas the light rays which are shown over here, they are coherent and incoherent light. So coherent sources of light are those sources which emit a light wave having the same frequency or wavelength and in same phase. So this is most important characteristic of coherent light, that the phase difference between the light rays, that will be zero. In addition to that, you have to see this particular point very carefully. If you have two independent sources, suppose you have two sodium lamps, it means you have two similar type of sources. So if you have similar type of sources, then you will get the similar type of wavelength from those sources, means light will be monochromatic. But if the sources are independent, then the light which is emitted from those independent sources, then that light can never be coherent in nature. So why I'm saying the light emitted by two independent sources can never be coherent in nature? The reason is initial phase of each and every source that is totally independent of each other. So what I'm trying to say here, if you have a light source, then you have billion of electrons in that particular source, and most of the electrons of that particular source will try to remain in a more stable energy state, that is ground state. But a few will be there in excited state, and the excited state that is having a very, very small lifetime, and order of that lifetime is approximately 10 raised to power minus 8 seconds. So after this particular time, there will be an automatic transition from this excited state to ground state. So when this transition will take place, you will get photons, and those photons are actually appearing in the form of light. So all the ordinary sources, they are giving us light through this transition from excited state to ground state. But if you have two independent sources and at a particular instant of time, you are getting certain transition in that particular source, then it is not necessary that you will get similar type of transitions in other source, even if that source is similar type of source. That is the reason I have mentioned here that if we have two independent sources, then we can never get coherent light from those sources. So again, I am repeating the reason. The reason is the initial phase of each and every source is totally independent of each other. So if there is any change in the phase of one of the source, you cannot get the similar type of changes in the other source. So now the question arises, if we cannot get coherent light from two independent sources, then what are the methods through which we can get coherent light? So in the next slide, I will explain that how you can get coherent light. So if you want to get coherent light, then what you have to do? You have to divide a single source into two parts. So if a single source is divided into two parts, and from those two parts you are getting coherent sources, it means those two coherent sources which are obtained from a single source, those two must have same frequency. So if you have coherent light, then it is necessary that light will be monochromatic. But if light is monochromatic, then it is not necessary that light is also coherent. So you have to understand this particular statement, that if light is coherent, then it is very necessary that light will be monochromatic in nature. But if light is monochromatic, then it is quite possible that you have two independent sources and you are getting monochromatic light from those two sources. But it is not necessary that you are getting coherent light from those two sources. So how we can get coherent light? So in this slide, we will see the methods to get coherent light. So basically there are two methods to get coherent light. The first one, that is known as division of wavefront. So in this particular method, just by dividing the wavefront of light, we will get coherent sources. And you all have seen that Young's double slit experiment in your lower classes in physics, where you have seen that a single slit that is divided into two parts, that single slit will illuminate two slits. You can see here, you have a monochromatic light source. From that monochromatic light source, this particular slit is illuminated. Then two slits are there, S1 and S2, which are kept at an equal distance from this single slit. So by the division of wavefront, these two slits will act as two coherent sources. So this is example of Young's double slit experiment. So this is one method to get coherent light. Examples of division of wavefront are also this Lloyd's mirror method. This is also example of division of wavefront, where by the division of wavefront we can get two coherent sources. Fresnel biprism experiment, where two acute angle prism are joined together, and then you will get two virtual coherent sources by the division of wavefront there. So division of wavefront, that is one example, that is one method to get coherent light by dividing a single source into two parts. Another example is division of amplitude. Division of amplitude means you have a light source. From that light source you are getting light rays. then the amplitude of those light rays, that is further divided into different rays. Then all these rays, then they will get superimposed and you will get an interference pattern due to those coherent rays. Why I'm saying the rays which are coming from a single ray, they are coherent in nature? Because if there is any change in the phase of your parent source, you will get the similar type of changes for all the rays which are obtained by the division of amplitude of a single ray. So division of amplitude, that is an example of getting coherent sources. Another example in addition to division of wavefront. You all must have seen soap bubble in the presence of sunlight. So when you will see a soap bubble in the presence of sunlight, you will get beautiful colors in that soap bubble. So basically those colors are obtained because of interference of light. And in that soap bubble, you are getting interference of the coherent rays which are obtained due to division of amplitude. So division of amplitude is having different examples, like Newton ring experiment, that is best example of division of amplitude. So these are the two methods to get coherent light. Now there are two aspects of this coherence. Means if you have a light source, from that light source you are getting light radiations. Now along the direction of propagation and in a direction perpendicular to propagation, we have two type of coherences. One coherence which is along direction of propagation of light, that is related to time, and that is also related to monochromatic behavior of light. The other type of coherence which is actually obtained in a plane perpendicular to direction of propagation, that type of coherence is actually related to distance. And this particular coherence, in other words, we can also say that second type of coherence which is in a plane perpendicular to direction of propagation, that is also related to size of the source. So two different types of coherences are there. The first one is known as temporal coherence. Temporal coherence, this is also known as longitudinal or axial coherence. And the second type of coherence, that is known as spatial, transverse or lateral coherence. This first type of coherence, that is in a direction parallel to, that is obtained in a direction parallel to direction of propagation. Whereas spatial or transverse coherence, that is in a plane, that is defined in a plane perpendicular to direction of propagation. So what is the exact meaning of this temporal and spatial coherence? That we will try to understand in our next slides. So this temporal and spatial coherence, these both type of coherences, they are seen in Young's double slit experiment as well as in Michelson-Morley experiment. So in these two examples, you can see both type of coherences, that is coherence in time as well as coherence in space. So the first type of coherence, temporal coherence. So in case of temporal coherence, what you have a light source. If you have a light source, from that light source you are getting light radiations. Suppose these light radiations, they are propagating along this direction. Now in this direction of propagation, we have taken a plane. In that plane, there are 2 points. Let one point is x and the other one is y. Now we will find the phase difference between those 2 points at time t1, and in addition to that, we will also find the phase difference between those 2 points at any other time t2. Means there are 2 different times, one is t1 and other one is t2. At these 2 different times, we are going to find out the phase difference between that x and y, between those 2 points which are present in a plane parallel to direction of propagation. If the phase difference between that x and y is not changing with time, means if the phase difference between x and y, let that phase difference is delta phi at time t1, and if at time t2, if that phase difference is delta phi dash, and if both the phase differences are equal, then you will say there is temporal coherence between x and y. So I am repeating it again. What you have a light source. From that light source, you are getting light radiations. This is direction of propagation of light. Along the direction of propagation, you have a plane. In that plane, there are 2 points. And if the phase difference between those 2 points is independent of time, then you will say there is temporal coherence between those sources, right? So basically this temporal coherence that is related to the monochromatic behavior of the source, means more the monochromatic behavior of the light source, more will be the temporal coherence for the source. So let's try to understand the meaning of this temporal coherence. So now you can see in this picture, you have a light source. Since I have already explained that if we have a light source, then we will get perfect sinusoidal radiations from that particular source. If you have an ideal source, then that ideal source can maintain this perfect sinusoidal behavior for infinitely long time. But you know, in practical sources, after a certain time, there will be a break in phase. Now, if this is direction of propagation of light, suppose we are taking 2 points, one at this particular position, and suppose that second point is present over this particular position, and these 2 points, they are in a plane parallel to direction of propagation. Now what we have to do? We have to find the phase difference between these 2 points at time t1, and let that phase difference is phi b minus phi a. Then at time t2, again we will find the phase difference, and if that phase difference is phi b dash minus phi a dash, if these two phase differences, if these two are having same value, then we will say there is temporal coherence between A and B. So that is explained over here, that at time t dash, at time t, phi b minus phi a is the phase difference, and at time t dash, phi b dash minus phi a dash is the phase difference. If that phase difference is not changing with time, then there is temporal coherence between the light sources. And if the phase difference is different at these two different times, then we will say there is no temporal coherence between A and B. So if we have ideal source, as I have already explained, for ideal sources, this coherence time, the time up to which you will get perfect sinusoidal behavior, that coherence time is infinite. Whereas for real sources, in practically the sources which we are having, they cannot maintain this perfect sinusoidal behavior for infinitely long time. Those sources can maintain that behavior only for a particular duration, only for a finite time. Means that coherence time for real sources is always having a finite value that can never be equal to infinite. So that is explained over here. So this is the meaning of your temporal coherence. Now there are different parameters which are related to this temporal coherence. So this is also explained over here. Light is propagating along this direction, and along this direction 2 points are taken. Then phase difference between those 2 points is observed at 2 different times. If that phase difference is not changing with time, we can easily conclude that there is temporal coherence between these 2 points. So you can see here perfect sinusoidal behavior. This perfect sinusoidal behavior for real sources that will be maintained for infinitely long time. But for practical sources, for real sources, this temporal coherence, this perfect sinusoidal behavior along direction of propagation is only for a finite time. As I've already mentioned, that temporal coherence is also known as longitudinal coherence. And this temporal coherence is also related to monochromatic behavior of the source. Now, how can we say that temporal coherence is related to monochromatic behavior? So, whenever we are saying we have a monochromatic light source, monochromatic means the light source is having a single wavelength. But even if we are having a monochromatic light source, suppose I am taking one example. Suppose we have sodium light. Sodium light that is having a yellow color light, and you will get 2 different wavelengths from that sodium light or sodium lamp. One is having wavelength 5890, and other wavelength which is coming from that sodium lamp is 5896 angstrom. Since those 2 lines which are coming from sodium lamp, they are having a very small difference in their wavelength. So, for practical purpose, we can assume that the wavelength coming from the sodium lamp is average of those 2, that is approximately 5893 angstrom. So, that sodium lamp is not strictly monochromatic. But since the difference is very small, we can say that sodium light or sodium lamp, that will give us monochromatic light. So this is true for all the practical sources. Whenever you have a light source giving you a certain wavelength, giving you certain light of particular wavelength, so in addition to the most intense line, you will also get few lines around that particular central line. Means there will be a bandwidth, there will be a spread of wavelengths around the central lines of central most intense line for any particular source. So that is known as bandwidth. If you have an ideal source, ideal monochromatic source, then that bandwidth is very, very small, and for ideal cases this bandwidth is 0. But practically this delta nu is not equal to 0, that is having certain value. So this particular bandwidth is actually related to temporal coherence. So that you can see over here, we have two parameters. One is coherence length and other one is coherence time, which are related to temporal coherence. Coherence length is actually the distance traveled by the light in coherence time. So if we are saying light can maintain perfect sinusoidal behavior for this time, so in this time the distance traveled by the light is known as coherence length. I am repeating it again. The coherence time is that particular time up to which we will get perfect sinusoidal behavior. In that coherence time, the length traveled by the light, that is known as coherence length. So that is the meaning of coherence length and coherence time here. For light, we know that product of frequency and wavelength, that is always equal to C. So from here you can see that delta nu is equal to minus C delta lambda upon lambda square. So if you will write the magnitude of this delta nu, that is the bandwidth here. This magnitude is C delta lambda upon lambda square. So basically this coherence time is inverse of this bandwidth. You know the relationship between frequency and time. So this coherence time of any light source is actually the reciprocal, the inverse of bandwidth of the source. So smaller the value of delta nu, you can understand from here, smaller the value of delta nu, greater will be the coherence time. Means greater the monochromaticity of the source, greater will be the temporal coherence. It means more monochromatic is the light source, for longer time we can maintain a perfect phase relationship between 2 points which are present in a plane parallel to direction of propagation. Means temporal coherence, that will be higher, coherence time, coherence length will be higher if the bandwidth is smaller. So that is the reason we can say the temporal coherence is related to monochromatic behavior of the light source. So if you will substitute this value of delta nu here, you can see Tc is equal to lambda square upon C delta lambda. You can see that all other parameters are fixed. So this delta lambda is the deciding factor. Smaller the value of delta lambda, greater will be the coherence time and greater will be the coherence length. So that is the reason we can conclude that temporal coherence is related to monochromaticity of the source. Coherence length, that is equal to C times Tc. And we have already seen in the previous equation that your Tc is lambda square upon C delta lambda. From there you are getting your coherence length is lambda square upon delta lambda. Smaller the value of delta lambda, greater will be the coherence length. So it means smaller the value of delta lambda, greater will be the coherence time as well as coherence length. There is one more parameter which is used to define this temporal coherence, and that is known as spectral purity or quality factor. So the spectral purity is actually defined as lambda by d lambda, and this LC, which is lambda square upon delta lambda. So if you will divide it into two parts, the first one is lambda by delta lambda and other one is lambda. So you can see here this lambda by delta lambda is spectral purity factor. So this LC can also be represented in terms of spectral purity factor as Q into lambda. So you can see this temporal coherence in this Young's double slit experiment. So you have the single slit which is illuminated by a monochromatic light source. Then by the division of wavefront, these two slits are illuminated. From these two slits, two light rays are coming. Suppose the first one is coming from slit S1 and the second is coming from slit S2. and these two, they are reaching at this particular point P. Now, since these S1 and S2, these two slits will act as two coherent sources because they are generated from same source. Now, the source which is illuminating these slits, that source is also having a coherence time. Coherence time means this particular source is having a finite time up to which we can get perfect sinusoidal behavior. If the first ray, that is taking time t to move from S1 to P, and the second ray, if it is taking time t plus delta t to move from S2 to P, then the time difference between these two, that time difference is delta t. So if this time difference is less than or equal to the coherence time of the source, only then there will be a perfect phase relationship between ray 1 and 2. Means only then these two rays will be coherent, which are coming from S1 and S2. Only then S1 and S2 can give you coherent light if the time difference between 1 and 2, if that time difference is either less or equal to coherence time of the source. So that is the meaning of your temporal coherence. So up to now what I have explained that coherence means perfect phase relationship, either zero phase difference or constant. Coherence that is of two type, but before that, if you have two independent sources, then those sources can never give you coherent light because the initial phase of each and every source is totally independent of each other. So what are the methods to get coherent light? One is division of wavefront and other one is division of amplitude. After that, I have explained about temporal coherence, which is actually related to time, and the second type of coherence that is related to space, which we will discuss in our next lecture. So lastly, we have these reference books which you can refer to understand this particular topic of coherence. So that's all for today. Thank you very much.